The structure of the Sun. The Sun is a massive nuclear power station which lights and warms our planet. It is a massive ball of burning gas, but has a remarkably complex internal structure. The energy is produced in the core of the Sun, but takes millions of years to reach us here on Earth. This animation describes the interior of the Sun and the nuclear reactions that occur at its heart. The Sun contains 99% of the matter in our solar system, most of which is hydrogen. It is powered by nuclear reactions that take place at its core, producing vast quantities of energy and other chemical elements, such as nitrogen, carbon, oxygen, sodium, potassium, calcium, and iron. At 150,000 kilometers across, the Sun is not a simple ball of hot gas, but has a complex internal structure that scientists have divided into 8 separate zones: the core, the radiative zone, the interface layer, the convection zone, the photosphere, the chromosphere, the transition region, and the corona. The density and temperature of the Sun varies dramatically from the core to the surface. At its center, the Sun is so dense that an amount the size of a glass of water would weigh the same as an adult woman. It is so hot that normal matter cannot exist. Atoms are broken down into a soup of nuclei and electrons, and chemical reactions cannot take place. The core is the hot, dense region of the Sun where nuclear fusion reactions take place. The nuclei of atoms are squeezed together so hard that they fuse and form larger atoms. As they do so, they lose a small amount of mass, which is turned into energy, according to Einstein's famous equation E = mc². If you took just 1 gram of this matter, equivalent to a pinch of sand, and converted it into energy, you would produce sufficient electricity to boil about 10 million kettles, enough for a cup of tea for the whole population of the UK. The main nuclear fusion reaction in the core of the Sun has 3 stages. First, 2 protons fuse to produce a nucleus of deuterium, releasing energy in the form of a positron and a neutrino. Next, the deuterium fuses with the further proton to produce a nucleus of helium-3 and a high-energy gamma-ray photon. Finally, 2 helium-3 nuclei fuse to produce 1 nucleus of helium-4 and 2 high-energy protons. The radiative zone is marked by a significant drop in both density and pressure. The density drops from about 5 times that of pure gold to 1/5 of that of water. The drop in both temperature and pressure means that nuclear fusion reactions can no longer take place. Instead, the energy released in the core starts to make its way to the surface of the Sun. Energy is released in the core of the Sun in the form of photons of radiation, such as light, X-rays, and gamma rays. These have to make their way through the radiative zone, which is a densely packed mass of hydrogen and helium nuclei, plus free electrons. It is so crowded in the radiative layer that it takes each photon nearly 3 million years to reach the interface layer, a distance of around 300,000 kilometers. A photon would take just 1,000th of a second to travel that distance in empty space. The interface layer is a relatively thin layer that marks the transition from the radiative zone to the convective zone. It is not a hard, well-defined layer, but moves constantly as the radiative zone below and convective layer above swell and shrink. The temperature of the convection zone drops to about 5,700 degrees centigrade. At this temperature, electrons and atomic nuclei can start to recombine into atoms, though it is still too hot for the majority of molecules to stay together. The density drops dramatically to greatly below that of the Earth's atmosphere. Energy from the interior of the Sun moves through the convective layer as heat, rather than as photons. Heat is just movement of atoms. The faster the speed, the hotter the atoms. Heat is transferred from atom to atom in a process called convection. Hot atoms hit cooler ones, speeding them up. The hot atoms transfer some of their energy to the cooler atoms, as if passing the baton in a relay race. The photosphere is hotter than the edge of the convection zone and is where most of the light we see from the sun originates. The photosphere's density is very low, much lower than the Earth's atmosphere. The hot gas glows brightly in the same way as the gas inside a fluorescent light bulb. The photosphere is often thought of as the surface of the sun, as it is the part that we see, but the sun has no true surface. It's just that we cannot see deeper into the sun without special instruments. Sunspots are darker patches on the surface of the sun. They are darker because they are cooler. Sunspots come and go in regular 11-year cycles, with many visible at the peak of the cycle and often none visible at the minimum. They are caused by regions of magnetic flux within the photosphere, like the two poles of a horseshoe magnet. Sunspots are thought to have an influence on the Earth's climate, but exactly how this happens is still unclear. A solar flare is a massive burst of gas which shoots off from the sun's surface from time to time. The magnetic fluxes which link sunspots carry gas from one part of the sun's surface to another. Under some circumstances, these magnetic fluxes can become twisted, and instead of the gas returning to the sun, it is shot off into space. Solar flares can have a big impact on Earth. The huge amount of energy they carry can disrupt power grids and knock out satellites. Industries vulnerable to solar flare activity receive regular solar weather forecasts so that they can have advance warning of a solar flare reaching the Earth. The chromosphere and the transition region are much hotter than the layers underneath, reaching about 1 million degrees centigrade. It is still a puzzle why this should be so. Scientists have offered a number of explanations over the years, but there is still no general agreement on what causes this phenomenon. The chromosphere is often likened to the sun's atmosphere, but this description should be used with caution, as the sun does not have a hard surface for an atmosphere to sit above. The transition region is a relatively thin layer above the chromosphere. Above the transition region is the corona, the last layer of the sun, which is made up of hot, diffuse gas that can stretch up to 150,000 kilometers from the photosphere. You can only see the chromosphere and the corona during a solar eclipse, when the moon blocks out the light from the photosphere, leaving the chromosphere and corona visible as a halo around the sun. The outer part of the corona is considerably hotter than the layers beneath it, which is a puzzle. The only heat source is the sun below the corona, so it would be expected that the outer layers would be colder than the inner layers. The two main theories to explain coronal heating both require energy to be transferred from the sun to the coronal gas. The first theory is that waves, a little like sound waves, travel through the corona carrying energy into it from lower down. The second theory is that large numbers of small solar flares carry energy into the corona. The corona is made of superhot gas called plasma. From time to time, pairs of sunspots form in the photosphere, linked by magnetic flux. These can drag cooler plasma from the photosphere into the hotter corona, where they are suspended by magnetic fields, producing a prominence. In time, the magnetic fields become unstable, collapse, and the prominences disappear.